Good morning everyone, I am Alessia and I'm going to present an overview about the importance, classification, standardization and fair management of modeling data. I am a researcher at the Department of Electronic Engineering of the University of Rome Tor Vergata, and I am involved in the Challenges project as the representative of TIBER-Lab. My background is about computational material science, and my research field is the modeling and simulation of materials for optoelectronic devices. I will start this webinar introducing the topic of modeling data, highlighting the importance of materials modeling and simulation for both the academy and the industry, and focusing on the need for a standard vocabulary describing modeling data and enabling the findability, accessibility, interoperability and reusability of modeling data as required by the European guidelines for scientific research projects. Modeling is a powerful tool to support materials research. It provides the key information for identifying new materials, tailoring materials, and design materials for novel or improved applications. Modeling and simulations support the experimentalists, helping them to access information that would not be available otherwise, and helping to interpret the experimental results. Moreover, modeling provides predictions on the evolution of a system in a quicker or cheaper way than with trial and error methods. That's why industry uses modeling to establish a strategy for testing and screening new materials when a try and fail approach cannot be carried out in the industry, or it would be too complicated, dangerous and expensive. Industry uses modeling also to understand results of measurements. This is particularly important at the nanoscale, where access to materials properties is often difficult. In this case, the simulation can provide information for every point in a sample at every time. And notably, industry uses modeling to reduce the time to market by accelerating the understanding and development of new materials or existing materials in new applications. In fact, modeling can suggest new materials and experimental procedures to create them, and can be used to examine the properties of materials and devices that have not or cannot yet be created. So, the industrial application is the target of materials modeling, and the key point for modeling in industrial application is the formulation of models that produce realistic results. A huge effort is dedicated to move from model development to model application and finally to industrial application, and this requires strong interaction between code development, validation processes and industry, and between the different modeling communities. In order to allow the proper interaction between these different communities and subfields, the modeling data must be findable, accessible, operable, and reusable. And this fair data management requires a standard and semantic classification of simulation data. So, first of all, it is important to define the necessary concepts employed in materials modeling and to classify models according to these concepts. Then it is important to choose standard names for these concepts, which harmonize the language of modeling subfields. This common language enables dialogue and mutual understanding between industrial end users, software developers, and theoreticians. This common language forms the basis for an ontology with a formal language of materials modeling and a definition of the relation between the concepts. Such an ontology can then be a basis for metadata and databases development, that is necessary for a modeling marketplace. Now let's see the definition of metadata. Metadata are a sort of vocabulary for describing the data. So metadata are data that describe and give information about other data. Metadata can be used to describe models, databases, and platforms, and all the concepts important to describe models and modeling data. As I said, the starting point is the terminology and classification that describes all aspects of modeling and simulation, so that we can move towards a semantic level of interoperability. Metadata are standard terms that allow interoperability. Metadata enable the exchange of information between different codes. In fact, data in databases should be put in a form that allows models to properly recognize data along with their meaning, and this can be done based on semantic metadata. Metadata can deal with the complexity of sharing data between different tools, and metadata can also be used for validating correctness, avoid confusion about types, units, dimensions, and automatize configuration of import-export file filters. Another aspect is how to make the data available. Simulation data are, in fact, encoded in documents containing text, tables, images, and metadata and databases allow modelers to publish their simulation data in a structured and semantic way, and that will enable others to find and reuse the data. So, metadata and databases make it possible to do science in a collaborative way. I want to highlight that all the material presented in this webinar is based on the review of materials modeling, reported in the book What Makes a Material Function? Let Me Compute the Ways. This is a public document that describes the terminology for modeling data and classification of models and simulations as required by the European Commission. Moreover, I want to highlight the importance of the European Materials Modeling Council that brings together all the relevant documents, events, and communities involved in the standardization of modeling data. This is how the data documentation section of the European Materials Modeling Council website looks like. You can find here the link to the review of materials modeling, to the workshop agreement about terminology classification and metadata, and the link to the so-called MODA, that is a template for the documentation of simulations. Before going through the MODA template, I want to describe the basic concepts for modeling and simulation and their new terminology and classification. Now, it is not always clear whether expressions used by modelers to describe their work deal with the entity, the physics equation, the closure relation, the solver, the input, and sentences are not always precise enough. So, as I said before, we have to first define concepts used in simulations. Then we have to choose words for these concepts, that is the vocabulary. And finally, we have to do a classification that is based on these concepts and highlights the physics. Materials are complex systems, and the equations that describe the physical and chemical behavior of real systems are often too complicated to be solved. So the description of phenomena has to be simplified. Not all the details need to be taken into account to reproduce experimental results or predict the behavior of a system. Key assumptions must be made, ignoring the complexity that is not necessary to describe the given situation. So we use approximated equations describing generic physics. The physics equations are by their nature generic and widely applicable, and this is the strength of modeling. But of course, a physics equation alone cannot be solved. The equation has to be applied to a specific case documented by the materials relations describing a specific material. The physics equations plus materials relations are called model. It is the definition of model. And let's see the definition of simulation. Simulation gives the numerical solution to the model applied to a specific situation. Now, materials models were usually presented by the length and time scales of their applications, but as computers grow, the application areas started to overlap, and the application area is no longer a good identifier of the model. So, in the new classification, models are defined by the entity whose behavior is described by the physics equation. In the review of materials modeling, 4 entities are identified. Materials described by models consist of either electrons, atoms, nanoparticles, or are considered as a continuum. The entity itself is considered to be frozen, and processes inside are not resolved. So, based on the entity whose behavior is described by the physics, 4 classes of models are defined: electronic models, atomistic models, mesoscopic models, and continuum models. Now, it is the modeler who chooses to describe a certain phenomenon employing a certain model. If very high accuracy is needed, an electronic model is applied, but often solving this model requires too much computational resources, and a less accurate continuum model is used. So, user cases to be calculated should be described without any modeling information, and then different modeling approaches can be benchmarked. Electronic models are physics equations describing the behavior of electrons. The theoretical framework of most electronic models is the Schrödinger equation, with which the evolution at the quantum level of any atomic or molecular system with time is described. The electronic wave function is a function which represents at each moment in time the positions, momenta, and spins of all electrons in the system. The most crucial element is the Hamiltonian operator, which represents the total energy of any given wave function and takes different forms depending on the forces acting on the material. A model based on the Schrödinger equation approximates either the Hamiltonian operator or the wave function of the quantum system. To solve the Schrödinger equation numerically, the concept of basis sets of wave functions is introduced. The orbitals are expanded as a linear combination of such functions with the weights or coefficients to be determined. Often, a simple and effective basis set is made of linear combinations of atomic orbitals. In solids and other systems that can be represented by a unit cell with periodic boundary conditions, it is sometimes more appropriate to use basis sets composed of plane waves up to a cutoff wavelength. These functions are naturally periodic and independent of the atom positions and are therefore appropriate to describe the delocalized electrons in solid crystals. Atomistic models are physics equations describing the behavior of atoms. When the electronic degrees of freedom are ignored, molecular mechanical models and classical mechanics are applied to describe the behavior of atoms and molecules. Newton dynamics can be used to describe active interactions between atoms, called force fields or interatomic potentials. Interatomic potentials do not treat the quantum nature of electrons explicitly, which allows models using these potentials to be enormously faster than models using quantum methods. Such interatomic potential-based modeling may not be as accurate as full quantum mechanical approaches, but can be used to simulate complex materials processes. Atomistic models can simulate the behavior of molecular systems, maintaining individual atomistic detail, but removing an explicit representation of the electrons, and although the application systems are not always large enough to be considered macroscopic, they are often sufficiently large to reproduce experimental results within the desired accuracy and, at the same time, detailed enough to detect their microscopic origin. Mesoscopic models are approximated physics equations describing the behavior of entities like nanoparticles, grains, large biomolecules, or macrospins. These particles are considered to be frozen and the detail inside is not resolved. The models can be applied to entities consisting of hundreds up to unlimited number of atoms, particles with length scales from tens of nanometers up to millimeters, and the phenomenon could have time scales from milliseconds to several seconds. The length scale of the entity does not determine the type of model. If the inside of the entity is not resolved, then it is a mesoscopic model. Molecular models, if they group more than one atom together in an entity, belong to this class of models, describing the behavior by a physics or chemistry equation. For example, in order to speed up the calculations, in certain cases certain atoms may be combined and considered as one entity. These are called united atom force fields, and some atoms, like hydrogen and carbon atoms in methyl groups, are treated as a single unit. These mesoscopic models need as input materials relations, which give the description of forces between the particles. Potentials and force fields for mesoscopic interactions are defined in a similar way as for atomistic potentials, and their output is the position and velocity of the entities. Concerning continuous models, we have to say that modeling for materials design with desired macroscale properties is about investigation of relations between chemical composition, microstructure, and effective properties. Materials are composed of molecules separated by empty spaces. Physical and chemical processes at the smallest scale are modeled by electronic, atomistic, or mesoscopic models. However, certain physical phenomena can be modeled assuming the materials exist as a continuum, meaning the matter in the body is continuously distributed and fills the entire region of space it occupies. And these are continuous models, approximated physics equations describing the behavior of continuum unit cells. The entity in a continuous model is the continuum material. Numerically, this is divided into finite volumes, and sometimes instead of saying that the continuum material is the entity, we call the finite volume the entity, but this is not true. The length scale for the numerical entity modeled in continuum models has two limits. The lower limit is related to the notion continuum, and this lower limit is so big that even heterogeneous materials can be considered to vary in a continuous fashion. Upper limit is related to the requirement that the model describes reality, and this upper limit is thus smaller than any spatial variation in material properties. Now, let's see how different classes of models can be used to describe the macro behavior of materials including the smallest details. First of all, if we look at the number of projects that use one of the four main types of electronic models, we can see that ab initio models are the most popular. This is because ab initio approaches do not need input parameters, and the output of ab initio simulations can be used to develop parameters for the other models. This means that we can incorporate quantum effects into larger and more realistic simulations, reducing computational effort. And this is the concept of multiscaling, the art of choosing the right model and model workflow. In order to increase their capability and applicability, continuum models need to be supplemented with descriptions of processes which originate at the electronic, atomistic, and nanoparticle scale. So the great challenge in creating accurate and predictive models is that materials form a true multiscale problem that is a consistent workflow of simulations at different levels of representation that allows the description of macro behavior of materials, including the smallest details. The scientist has to choose which models to use, investigating which physics is needed to describe the given situation, and depending on the balance between accuracy and simplicity. That is the most important part of modeling. A particular user case can be described by many different model chains, and these approaches can be benchmarked, and the standardized descriptions should facilitate this. An important example of multiscaling is the device simulation, where the electronic description of the material is integrated into the macroscopic behavior of the device using several models in a multiscale workflow, where the interaction between different models consists in the exchange of quantities and in the definition of boundary conditions, and experimental measurements or ab initio simulations are employed to provide input parameters for these models. The word method indicates the way in which models are used. This is the workflow describing how models are put into a chain and are simulated either subsequently or concurrently, and the workflow describes when and how to link in databases with experimental or simulated data. For sequential modeling, we use the term linking models, and this means running different models one after the other. For concurrent modeling, we use the term coupling models, and two types of coupling exist: the iterative coupling and the tightly coupled equations solved together. That means running different models for the same entity concurrently by solving one matrix. This is the template workflow to represent linked models, where the models are employed one after the other. An example of linking models is the study of elasticity in the framework of multiscale modeling applied to device simulations. In fact, in order to have the optimized atomistic structure with relaxed atomic positions, we have to employ an atomistic model, such as valence force field. But to initialize the model, we first have to run a continuous elasticity model. Continuous elasticity does not consider the internal structure of the unit cell, but only the deformation of the Bravais lattice. We thus precondition valence force field model by deforming the structure according to continuous elasticity. This is how the template workflow for iterative coupling looks like. The output of the first model is used as an input for the second model, and in turn, the output of the second model is the new input for the first model, and this process is iterated until a given convergence criterion is reached. An example related to device simulations is the self-consistent use of continuous models for potentials and electronic models for charge densities, where the potentials derived by Poisson drift diffusion models is projected on atomic positions to set up the Hamiltonian for the electronic model, and in turn the densities obtained by the electronic model are projected onto the finite element mesh for the continuous models, and this is iterated until convergence is reached. And this is the template workflow for tightly coupled models, that are tightly coupled equations solved together running different models for the same entity concurrently by solving one matrix. Here, an example related to the previous slide is the Poisson drift diffusion coupling. Let's see also the definitions of solver and post-processing. Simulation of models applied to new materials involves finding a solution to the equations of the model, and solvers are numerical methods used to solve the physics equation complemented by the materials relations. Note that in the review of materials modeling there is a strict separation between the concept of solver and the concept of model. For example, finite elements method is a solver technique. This method is used to solve physics equations in continuum models, and also for discrete models when continuum notions like distributions are used. But we have to keep in mind that this is a solver and not a model. Even statistical models, treating the many-entity system as a large statistical population whose behavior is determined by the forces applied to each single, are still classified according to the entity whose distribution they describe. Note that a common mistake is to speak about Monte Carlo as a model, but it is not. Monte Carlo is a statistical method to solve different equations. It is usually employed to simulate the time evolution of processes with a given known rate, and the rates are inputs to the Monte Carlo algorithm. So, the classification given in the review of modeling materials is simple, but it is not always easy to keep in mind that solvers are numerical methods, not models, and solvers do not determine the model class. Concerning post-processing, we have to say that a major issue in linking and coupling models is transfer of data from one model to another. Now, the operation of extraction of model output is called post-processing, but this can also be called pre-processing for the next model. Post-processing is an operation on the dataset resulting from the solution of the physics equation in order to extract useful information. This usually takes substantially less computing resources than the solver itself. This is because of the essential difference between a post-processor and a physics equation. That is, a physics equation calculates or generates a new physical system state, while a post-processor does not. A post-processor obtains more information about the same physical system state. There are many types of post-processors, like visualizers that read and visualize data. They do not change the data, they do not add further data. Converters change the numerical representation of a state without changing the physical state itself. Extractors enrich the state description by further information being calculated based on the information already contained in the state. For example, averages, interpolations, parameters, other physics quantities applying their definitions. For example, the electrical potential can be extracted from the charge distributions of the same state, as you can see in the figure, and the work function of a material can be determined by the difference between the vacuum potential and the Fermi level of the system state, and the work function can then be used as input parameter for metal contacts in device simulations. Finally, before going through the MODA template, I want to highlight the difference between model application and model development. We talk about model application when we apply an existing physics equation and materials relation to a specific situation. The tuning of parameters in these equations is not considered to be model development. However, the strength of physics-based modeling is that the physics is widely applicable. A model is strong if it is transferable from one material system to another within the limits of the model. So, applying existing physics and chemistry models to new materials and manufacturing processes generates new information. When we apply an existing model to a new situation, unexpected results or new phenomena may be discovered. So, model application is a paramount activity for industry, and consistent and transferable parameterization are paramount for the reliability and applicability of a model. And that's why a huge effort is dedicated to the post-processing of the output of ab initio simulations in order to extract parameters for the other models. On the other hand, model development is the act of finding the proper approximations in the physics equations and in the materials relations. Materials modeling is the establishing of governing equations containing the key assumptions of the model. Modeling starts with an approximation of the physics, which at first is seen as a good balance between complexity and computability. Then, development of models may either make the model more complex or reduce the complexity of the model. Sometimes, models cannot be transferred from one physical situation to another. In such cases, research projects may want to increase the complexity of the model by incorporating new physics and chemistry. Modelers start from strongly approximated physics equations and then add complexity until a reasonable agreement with experiments is obtained. Modelers more often establish new materials relation either from measurements or by applying models of a finer type and transferring the results into a coarser type of model in the form of relations with new terms expressing the added physics phenomena now accounted for. This allows them to identify the critical relevant processes that lead to experimental results. Adding new terms to include physical or chemical properties previously disregarded in the approximations will be considered as a new material relation and thus as a new model. On the other hand, the Schrödinger equation, Newton dynamics, and conservation equations are the foundations of materials physics and chemistry, but these equations can often not be solved, and an approximated equation is taken instead. Development of models may also reduce the complexity of an existing model if the accuracy allows it. This is done to save computer time, basically. A reduced model starts from a pre-existing detailed physical equation which is systematically simplified by using expert knowledge or machine learning procedures for extracting most relevant features. Now, let's have a look at the modeling data template for documentation of simulations. The information of models is very different in different fields. Sometimes modelers name the solver, sometimes the application or the length scale, and not always the complete physics is given. It is important to give information about the physics equations, the materials relations, the solver, and the post-processor for each model in the workflow, and the exchange between models. And we have to understand that it is important to collect the information in a standard way across all fields. That's why the MODA template has been developed. The MODA is meant to guide the documentation step by step, and by following this guideline, all necessary aspects will be presented. The aim of this template is to increase the information in project descriptions of modeling so that we can grow the field. The MODA will also help to inform the industry. The workflow pictures are very intuitive presentations of what modelers are doing, and the MODA will enable the later preparation of metadata and databases. Moreover, I want to highlight that the industry only wants validated models. Thus, the cooperation between modeling and characterization must be very tight. And it goes both ways. The interpretation of experimental data often relies on models as well. Deciding which physics to use in simulations relies on measurements to validate the model, and the post-processing of measured quantities into input parameters for modeling is widely employed. So we can say that the standardization of modeling data must be tightly coupled with the standardization of characterization data. This is how the template for modeling data looks like. The MODA contains a data element organization that is applicable to all materials modeling simulations. The MODA should contain all elements that are needed to describe a simulation. This information spans from end-user information to computational modeling details, but note that this is the overview of the simulation. It is composed of 5 sections, namely user case, chain of models, publication, access conditions, workflow, and its rationale. But for each model in the chain of models, that means in the second section, model 1, model 2, and so on, for each model in the workflow, we have a description document composed of 4 further sections, as I will show in the next 2 slides. Each model used in the simulation has to be documented in 4 chapters. The first chapter is dedicated to aspect of the user case or system simulated with this model. In the second chapter, the model has to be identified by its physics equations and materials relations. In the third chapter, computational aspects are documented, how the simulation specifications are translated into computer language. Finally, in the last section, post-processing is documented. How the output of one simulation is processed into input for the next simulation. That is the key point of model interoperability. Now I'll show you some example of workflow pictures. These are very intuitive presentations of what modelers are doing in the framework of some European projects that contributed to the review of materials modeling. For example, the project presented by this workflow aims to further develop the copper-indium gallium selenide thin film solar cell technology towards higher efficiencies by using novel approaches in passivation, patterning, and optical design. And we can see here a clear example of linking models. This workflow represents the DEEPEN project. DEEPEN focuses on new energy-efficient nanoscale electronic and photonic devices. Nanowires, nanoparticle arrays, and quantum wells are some of the large ensemble of new structures proposed for device applications here. This project developed an integrated multi-scale modeling environment particularly suited for studying electronic, transport, and optical properties of novel nanoscale devices. And we can see here a clear example of iterative coupling. This is only a detail of the workflow developed in the framework of the Lursenis project. The aim of the project is to develop long-lasting reinforced concrete for energy infrastructures used under extreme operating conditions. And I reported this detailed view as an example of tightly coupled models. Here I reported the workflow related to the StarCell project. The project targets the reduction of critical raw materials in photovoltaic cells and the optimization of the material processes and the device interfaces to achieve higher solar cell efficiencies. And we can see here how the post-processed output of the electronic model, specifically an ab initio calculation based on density functional theory, is considered a pre-processed input for the continuum drift diffusion model. To conclude, I want to remember the main references for the standardization of modeling data. That are the review of materials modeling reported in the document What Makes a Material Function? Let me compute the ways. As I said at the beginning of this webinar, all the material presented here is based on this review of materials modeling and on the information and documentation available on the European Materials Modeling Council website. And I thank you for your attention.